Welcome everybody to Geosciences Colloquium. It's my pleasure today to introduce the speaker, Professor Rick Bennett. So Rick received his PhD from MIT, and after that he did a postdoc at the Harvard-Smithsonian Center for Astrophysics. And while he was there, he transitioned to being on the research staff for a few years before he joined our department in 2004. So one of the long-running themes of Rick's work, both in his own and that of his students, has been using geodetic observations to understand deformation in Southern California. So particularly how strain is partitioned throughout the San Andreas fault system. He's also had a number of other projects with collaborators in kind of diverse settings, so including Iceland, Italy, the Basin Range, other areas. One of his current projects involves drilling a giant hole in central Italy in order to install some borehole strain meters there and study the ongoing deformation. Also in recent years, Rick has created the Accessible Earth fieldwork class in our department, and that takes students to Italy for a geophysics-focused field experience, but one that can accommodate students from a wide range of physical abilities. So in his talk today, he's going to be telling us about the state of stress in the crust, and particularly how it relates to earthquake aftershocks and what we can learn from that. So welcome, Rick, and go ahead.
Thanks, Chris. Okay, so can everybody see my first slide?
Yep, looks good.
Okay, great. Okay, well, thanks, Chris. So I just want to start off here by acknowledging my collaborators, Cassie Hannigan and Amanda Hughes in our department, as well as Lauro Chiaraluce at INGV in Rome. And so the topic today is about what we can learn about crustal stress and structure from aftershock focal mechanism data. There we go. Okay, so let me just get organized here a little bit. So I'll start off by giving an overview of the talk. Begin by trying to motivate the problem of determining the stress field in the crust. And a byproduct of this work is that we might be able to gain some information about crustal structure along with the stress, but here I'm going to focus mostly on the stress determination. I'll describe the approach that we've adopted to address some of the issues that arise in stress inversions, and then I'll move on to a case of a particularly interesting earthquake sequence, one that is in some sense well behaved in that our expectations are matched by our analysis. And then I'm going to move on to another example where the results at first glance seem a little peculiar, but once we dig into the literature a little, we find that the results are both consistent with previous studies and potentially alerting us to something interesting. Okay, so a foundational idea in active tectonics, and particularly in the subfield of tectonic geodesy that I live in, is that of the earthquake cycle. So the relative motion between the tectonic plates drives the accumulation of elastic strain near faults. And here you can see a depiction of the strain as the bending in the fence. Can you guys see my cursor?
Yes.
Okay, great, thank you. And the strain accumulation ultimately leads to the buildup of stress on faults sufficient to overcome the fault's frictional resistance. This leads to a rupture of the fault and rapid displacement during an earthquake, which reduces the stored elastic strain. During the earthquake, all or some of the elastic strain energy is recovered. In the cartoon, this is represented by the bent fence suddenly snapping back and becoming straight. And this is the primary process through which relative plate motion is converted into permanent deformation within continental plate boundary zones. Over many cycles, earthquakes contribute importantly to the development of the landscape and internal structure of the crust. So we would really like to be able to attribute many of the geologic features that we observe to the accumulation of regional tectonic stress, framing topography and crustal structure, deformation, and hazards in the context of plate tectonics in a truly quantitative way. However, despite the fact that the relative plate motion is steady over long intervals of time, millions of years or longer, continental plate boundary zone deformation is quite complex, with the brittle upper crust accommodating relative plate motion through a superposition of faulting and faulting rotations, all spanning very wide distribution of length, orientation, and time scales. So we have a look at the following image just to get a sense of the kind of complexity we're talking about. So this image is from the Skek community fault model, and showing known fault surfaces in Southern California together with seismicity. The faults are color-coded according to their strike directions, and the seismicity is color-coded by year. You can sort of make out the state boundary if you look at it long enough. And so we can use this image just to imagine the consequences of a large magnitude earthquake in the region. Large magnitude earthquakes change the state of neighboring faults. These changes in state can drive new patterns of seismicity, aseismic fault slip, pore fluid migration, viscoelastic relaxation, all of which contribute to the crustal stress field in some way, and thus to earthquake hazards. And importantly, stress changes are cumulative. And although some of these processes are diffusive by nature, stress perturbations from earthquakes can persist for decades or even longer, sometimes comparable to the time interval between earthquakes. And so although this model is complex, it's just a model. And real fault systems are certain to be even more complex, with fractures and internal fault structure at a scale that's hard to imagine with current techniques. Given this complexity, it's perhaps not surprising that most recent large magnitude earthquakes, such as the Landers earthquake, Hector Mine, Elmer, Kukupah, Ridgecrest, and others, have occurred next to, but not necessarily on, the faults that we thought were most ripe for an earthquake. And in addition to that, it's not particularly surprising that earthquakes are not periodic through time, as envisioned by the simple elastic cycle model that I showed in the previous slide. So to begin to understand this complexity, we need to move beyond the simple notion of an earthquake cycle as envisioned by Reed in 1910, shown here in part A of the figure. Clearly, the simple notion of elastic rebound needs to be modified, if nothing else, because it predicts periodic earthquakes. If we knew when the last earthquake was, we could predict when the next one would occur. That's clearly not possible. But as part B of this figure from Brodsky and van der Elst illustrates, there are two ways to create an earthquake. Earthquakes can arise due to increases in the stress acting on the fault, or to decreases in the effective frictional strength of a fault. Stress increases naturally due to relative plate motions, as the simple model in part A, but that's not the only way faults accumulate stress. Adding significantly to the complexity of the situation is the fact that earthquakes also transfer stress to neighboring regions. And so earthquakes can change the applied shear and normal stress on neighboring faults. A jump in stress caused by a large earthquake, here depicted by this jump F0 in the figure, might be sufficient to trigger another earthquake, taking the current stress level to that which is required to rupture the fault, exceeding the fault strength. And redistribution of stress also leads to post-seismic deformation, which may accelerate or decelerate accumulation of stress. That's depicted here, sort of changes in slope of this stress accumulation line. Local changes in the stress field may also lead to the redistribution of pore fluids, changing pore fluid pressure and thus the effective frictional strength of faults, so affecting this red line. And in some geologic settings, fault damage and fluid interactions can also lead to the development of fault materials with unusually low coefficients of friction over long periods of time. So there's a large number of compelling examples where main shock-induced stress changes affect subsequent seismicity. These range from the so-called shadow effect, as in the case of the Great San Francisco earthquake in 1906, after which the rate of earthquakes of magnitude greater than 6 fell appreciably from something like 2 or 3 per decade to something like 2 to 3 per century. So an order of magnitude difference shown up here. But less dramatic, but equally interesting are aftershocks, which tend to be organized in space and time following large earthquakes. By organized, I mean that we may reasonably predict the likely locations of aftershocks or the rates of occurrence, at least in a statistical sense, using physics-based or empirical models. So, for example, the figure on the bottom left here shows that we may predict with reasonable accuracy the likely locations of subsequent big earthquakes, like the Big Bear earthquake, as well as aftershocks. These tend to occur in places where the ratio of shear stress to normal stress is favorable for triggering, here indicated by the red colors. A curiosity regarding potential aftershock triggering mechanisms, however, is that earthquake-induced stresses are quite small relative to what we expect the tectonically accumulated stress in the crust to be. So the regional stress clearly plays an important role also. how do we know what the regional stress level is? The truth is that the background tectonic stress field is one of the more challenging physical properties to measure in the crust. Based on our understanding of fault friction, we might suppose that the crust is pervasively faulted everywhere and on the verge of failure. If so, we can infer stress levels under some presumed level of pore fluid pressure. It turns out that stress calculations assuming hydrostatic pore fluid pressure are consistent with the limited data we have on stress levels from borehole breakout data shown in the diagram on the top right here. The friction coefficient mu, that's a fault friction coefficient, inferred from this kind of stress analysis is also consistent with the classical experimental results of Byerly, which shows that friction values are in the range of 0.6 to 0.85 for most geologic materials. As these figures show, static stress is just a small fraction of the expected tectonic stress levels, at least for typical earthquakes in the continental plate boundary setting. So here we've got, of order megapascals or less, and here we have, hundreds of megapascals. So how is it possible that such small perturbations to the stress field can trigger aftershocks? Is the regional stress really orders of magnitude larger than static stress changes? Do aftershocks occur on planes that are optimally oriented with respect to the regional stress field? And is pore fluid pressure maintained everywhere at hydrostatic stress levels? So let's see if we can learn something about these questions from an analysis of aftershock focal mechanisms. Earthquakes are currently our best source of information about stress at depth within the crust. We can only drill so many holes and we can only drill so deep. But as I will elaborate on shortly, it's not possible to accurately infer stress from a single focal mechanism solution. In fact, it's common practice to invert focal mechanisms from several, maybe even thousands of earthquakes all at once to estimate a regionally average stress field. The assumption made in such studies is that the earthquakes sample the unperturbed stress field. There's some evidence that main shock-induced static stress changes can rotate the inferred stress field based on subsequent earthquakes. Thus, aftershocks are usually excluded from such analyses. And more recently, datasets, as datasets continue to improve, the community's begun seeking to determine a spatially and possibly temporally variable crustal stress fields. And so here's an example contribution to the SCEC community stress model from Yang and Hodgson, showing the directions of maximum horizontal stress as orange bars, these guys here. And in the color contours is normalized mean normal stress in the horizontal. And although this model contains a lot of detail and variability, the degree of stress heterogeneity in the real crust is still an outstanding question. The histogram shows that the distribution of maximum horizontal stress, and sorry, it kind of got clipped a little bit there. Aftershocks provide dense sampling over geographically restricted areas. So the question is, can we learn something about the stress field heterogeneity at a smaller scale from study of aftershocks? So let's think a few minutes about how stress is inferred from focal mechanism data. The starting point is the hypothesis that a triggered fault will slip in the direction of maximum resolved shear stress. This is known as the Wallace-Bott hypothesis. And it was proposed some 70 years ago. The cartoon on the left over here illustrates the idea. The unit slip vector S hat here coincides with the direction of maximum resolved shear stress indicated by tau hat. And this idea, it's got some support from the field of continuum mechanics. It provides some support for this idea in that alignment of the slip and the resolved shear stress directions here, slip and shear stress. You take the dot product between those two things. This dot product is largest when the two vectors are parallel to one another. And when those two stresses are parallel to one another, they maximize the efficiency with the slip reduces the stored elastic strain energy in the surrounding crust. Remember the bent fence. So if slip occurs in the direction of maximum applied shear stress, we could recover a straight fence profile more easily with the least amount of work. So this hypothesis should hold more or less independent of the triggering mechanism. So that is, it doesn't matter what started the earthquake. Once it's initiated, the fault should slide in such a way that it most efficiently reduces the stored shear strain energy. As mentioned, there's some evidence that large magnitude earthquakes can affect the stress field enough to influence subsequent stress field estimates. But there remains a lot of uncertainty regarding the conditions under which the static stress change will manifest as an apparent stress rotation. Okay, so this image is from the cover of a book from the late 70s, I think 1979, called Gödel, Escher, and Bach by Douglas Hofstadter. Was an essential read in the early 80s if you were alive at the time and nerdy enough to be interested in the newish field of artificial intelligence. Anyway, this image provides an analog, I think, to the problem of stress inversion. If you were given information only in the form of one of the projections, say G, then you would have really no chance of reconstructing the true shape of these blocks. However, given projections in different directions, say GE and all these different things here, then you might be able to reliably reconstruct the shape of the blocks. The stress inversion problem is like this in that we are given the directions of resolved shear stress, which are projections on fault planes, and we want to reconstruct the stress tensor. To do this, we need multiple fault plane orientations, meaning that we need multiple earthquakes to determine the stress field. So digging in a little bit deeper, things get a little bit messy. This is my most unattractive slide, I think, probably most messy one anyway. We seek to use the projected vector directions to reconstruct some properties of a tensor valued quantity. So for each aftershock, we have 3 direction cosines defining the unit slip vector S hat. And we seek to learn the 3 principal stress directions plus something about the relative magnitudes of the principal stress. So it's an inherently ill-posed problem if we're just going to try to use one focal mechanism to determine the stress. But if we use multiple slip vectors simultaneously, we can gain some traction. So the speed dating description of our approach to this problem is that we can think of the stress field as the sum of a homogeneous component superimposed by a contrast stress field. And so that's through the operation of some projection operators. So we have a homogeneous component that contains the stress averaged over the entire space. And then we have the contrast stresses. And to make the problem tractable, because still there we've actually made the problem worse, we have one stress at each aftershock location plus an additional homogeneous component. But we make the problem more tractable by using the k-means clustering algorithm from unsupervised learning algorithm to identify clusters of aftershocks that are in close spatial proximity to one another. And so aftershocks that belong to a cluster will be assigned a constant contrast stress. And the contrast stress field is modeled as constant within each cluster, but it can vary among clusters, and it's subject to the constraint that the sum over all the clusters is equal to 0 because it doesn't contribute anything to the average background stress. So then with modern data sets that contain thousands of aftershocks, we can reduce the stress inversion problem to finding k+1 normalized stress tensors. An important caveat is that the aftershocks probe the stress field only where the main shock induced stress field triggered the aftershocks, the red regions in the image over here. And the blue regions are places where the stress change wasn't sufficient to trigger earthquakes or even inhibited rupture. And so our approach is to attempt to resolve the stress tensor only in those regions for which we have data, as opposed to, say, gridding the entire region, as shown here. And trying to infer stress, a different value of stress within each grid cell. This is a very common approach, but I don't think one that's very appropriate for looking at aftershock data. For example, the aftershock data in the figure over here just doesn't tell us anything about the stress in the large blue region above Big Bear. So up here, for example, the cells that are labeled with X's. There's just no aftershocks there. There's no information about that. And if we were to try to somehow interpolate from regions where we do have aftershocks, we would grossly misrepresent the stress field in that region. So it's sort of like when you lose your car keys at night, you may have lost your keys in the park, but you might be inclined to look for them under the street lamp where you have a hope of seeing them. And this is in fact known as the street lamp effect or the street lamp bias. So, we acknowledge that this approach has this bias, but the truth is we have no hope of recovering stress in the regions where the aftershocks are absent or too sparse. And as a consequence, we just need to interpret any cluster contrast variability that we determine as a minimum total stress variability. Okay, so another important problem that we face is that we have to choose which of the two available focal mechanism nodal planes to resolve stress onto. There are several proposed methods for addressing this issue. One early concept was to resolve stress on the so-called optimally oriented planes. And those are the planes for which a given stress results in the maximum tangential shear stress. The argument for this choice is that the crust is pervasively faulted such that in any given location, a plane with optimal orientation is available for failure, and that's the one that would fail first. However, a detailed comparison of aftershock nodal plane picking strategies for different earthquake sequences was conducted recently by our very own PhD candidate and collaborator on this project, Cassie Hannigan. And among other important results of her work, she showed that aftershock nodal planes tend to be statistically distinct from optimally oriented planes. So aftershocks don't really seem to like the idea of optimally oriented planes. Many of you may have seen Cassie's work presented at AGU or GEODESY, so I won't go into much further detail here, but if not, you can read all about her work in a forthcoming paper. Another idea is to choose nodal planes that are deemed to be the most unstable in the given stress field. So you have two choices. One of them is more unstable than the other. This approach of Wawrzyk is illustrated in the more circled diagram here. In the denominator of this equation is the Coulomb stress resolved on optimally oriented planes, and in the numerator here is the Coulomb stress resolved on one of the given nodal planes. The idea is to choose the nodal plane that provides the biggest value here, which is the most unstable plane. One problem with this approach is that it presumes that both nodal planes exist in nature. You could have an earthquake on one fault. It has a nodal plane, but that doesn't necessarily mean that there's a fault associated with that nodal plane. So in this study, we aim to build on the work of Whelan and Sornay. I apologize if I mispronounced their names. They proposed the Gaussian mixture modeling approach to identify fault planes, which we'll describe in the next slide. The idea is that each mixture component represents a fault. And they used an iterative approach with cross-validation to decide how many mixture components or faults to include in their model. We take a similar approach, but instead we use a non-parametric variational Bayesian Gaussian mixture model. It's a mouthful. The bottom line is that we chose this approach because it chooses the number of planes for us automatically. So we don't inject more bias than we need to into our results. And so the basic idea of this mixture modeling is that aftershocks should reveal pre-existing crustal structure. The structure is complex, but may not everywhere contain faults in every conceivable orientation, such that the concept of optimally oriented planes isn't strictly applicable. And Whelan and Sornay considered several factors, including the distribution of along and across fault damage, distributions of microseismicity on known faults, fault rupture dynamics, and some other considerations. And they concluded that a mixture model approach is reasonable, with a mixture of Gaussians providing a useful combination of flexibility and functionality given current constraints on fault structure. This approach allows us to capture seismicity related to realistic fault structures encompassing the surrounding damage zone without restricting our attention to a smooth Euclidean fault core. So the typical sort of geophysical view of faults in the earth. And this is sort of a 2D version of what a fit to a subset of data might look like. We have groups of aftershocks associated with a 3D multivariate Gaussian distribution, and the eigenvectors associated with the smallest eigenvalue of the Gaussian covariance matrix represents the fault normal here. So the thin part of this, really eccentric ellipsoidal shape. And the other two eigenvectors are in the fault plane. So for our stress analysis, aftershock rupture planes are selected by this method, and then we choose the nodal plane that's closest to the overall sort of normal vector for the clusters or the Gaussian components. As we move forward, I'm going to present results from both for the heterogeneous stress from both Wawrzyk's code using the fault instability criteria to pick planes, and from our own code using this variational Gaussian mixture modeling. And these methods pick different subsets of nodal planes, but as you'll see, at least for the cases we've tested so far, they tend to produce nearly identical estimates for homogeneous stress. So that even if we're not 100% confident in the utility of this technique at this present time, it doesn't seem to matter. Okay, so we now have sort of the tools laid out to address some outstanding questions. First and foremost, we'd like to know the extent to which aftershocks can sense main shock-induced stress changes. Also, we might hope that the method can illuminate crustal structure by identifying aftershocks that are clustered in zones that could represent fault zones. But in the remainder of the talk, I'm going to focus on the first question by trying to glean as much information as we can about the post-main shock stress field from focal mechanism solutions. The second question about the distribution of aftershock focal planes is still in the development stage, and we hope to report on that in the near future. As a starting point, we acquired focal mechanism data from the 2019 magnitude 7.1 RIDGECREST, California earthquake sequence, and the 2009 magnitude 6.1 L'Aquila, Italy earthquake sequence. We have focal mechanism solutions for approximately 2,800 aftershocks of the RIDGECREST earthquake and roughly 3,400 aftershock focal mechanisms for the L'Aquila earthquake sequence. Here, we're only showing the focal mechanisms for the main shocks in the large 6.44 shock in the case of RIDGECREST to keep the plots uncluttered. But the seismicity, the locations of these aftershocks are shown by the pink dots here. So starting with RIDGECREST, the RIDGECREST earthquake sequence began in July 2019 and involves rupture on multiple intersecting orthogonal planes. The main shock or largest event in the sequence was a magnitude 7.1 earthquake with a surface rupture that spanned about 70 kilometers in length, striking northwest as shown. The distribution of slip at depth was determined from a combination of geodetic and seismic data sets, shown here. And so we use the slip distribution to compute static stress changes. By we, I mean Cassie has used this slip distribution to compute static stress changes associated with the main shock. And given this static stress changes, we are assured that the post-main shock stress field is heterogeneous at some level. The question is, can we sense that? And our aim here is to see what the effects of this stress change has on estimates for stress based on aftershock focal mechanism data. So this figure shows the distribution of aftershocks associated with the RIDGECREST sequence. The colors identify the different clusters that we put the aftershocks into according to our k-means clustering analysis, and the stars represent cluster centers. So in a sense, we can think of each cluster average stress as representing the stress at the stars. Oops. On the left is a map view, so north and east, and on the right here is a depth profile along strike. So this corner corresponds to this side, and this corner corresponds to that side. And we chose 60 clusters because that was the most number of clusters we could choose before things started to go a little haywire. The idea trying to be to capture as much of the stress variability as possible. So we began our analysis. We're going to start with looking at a study based on a simulation of aftershock focal mechanism data. So what does it require to simulate focal mechanism? We have to specify a regional stress field. And to the regional stress field, we can add the static stress change that we computed based on the main shock slip distribution. The magnitude of the regional stress is determined by assuming that the crustal stress is consistent with barrel friction and hydrostatic pore fluid pressure. And we also make use of previous stress studies which show that the largest principal stress is oriented approximately 5 degrees west and north, with the intermediate axis in the vertical direction. This is all consistent with Andersonian fault mechanics. We used the given earthquake locations and fault planes picked by the Gaussian mixture model. We applied the stress to the fault planes to predict the unit slip vectors according to the Wallace-Bott hypothesis. And then after computing the slip vectors, we added white noise with standard deviation of 10 degrees to the fault strikes, dips, and rakes to make a realistic simulated data set. Okay, so from these, we needed to compute the fault planes, and this is just a comparison of the picks that the Gaussian mixture model provides versus the picks that the fault instability criteria of Fabricic picks. And although the two methods tend to pick the same planes only about 50% of the time, so a flip of the coin would have done just as well, the density plots here demonstrate overall the planes that are selected have similar distributions, at least on average, which is interesting. The green line here represents the fault itself, so nearly vertical fault striking something like 135 degrees. And this triangle here represents the normal or pole to that fault plane. We can also look at the slip vectors. So once we pick the planes, we have the slip vectors. This depends both on the picks of the fault planes and on the simulated stress. And for both techniques, again, despite the fact that the planes tend not to be exactly the same, the distributions of slip vectors tend to be quite similar. And here again, the green line represents the fault, and the green circle is the slip vector associated with the main shock. And so in running the inversion code on simulated data, we of course want to make sure that our code works as we think it should. So we have some obligatory figures showing residuals and fits to data. In particular, this figure shows the observed slip vectors. Again, it's unit vector, so ranging between -1 and 1, so it's kind of an odd distribution. The modeled slip vectors, and then the residuals. The points are colored according to the cluster that they belong to. And so you can see, for example, that some clusters may have larger residuals than others, but overall, the statistics are reasonably satisfying, as we'll see also in the next slide. So we've got a variance reduction of 0.76, which is not too bad. And so this figure on the left shows a histogram of the residuals, where we can see that the mean mu is 0 or very close to 0. And the distribution is approximately Gaussian. I didn't actually check it to see how Gaussian it was, but it's got a Gaussian-esque look to it. It was good enough for me. Also on the right, we show the distribution of the dot product between the observed and modeled slip vectors. We're given unit vectors, basically directions, and we're trying to infer directions. So dot products seem like a good way to compare the two. And in a perfect world, we would expect the dot products all to be 1. If they're perfectly aligned. The distribution of dot product shows that we're close to this ideal on average, despite some complexities in the inverse problem. There are some exceptions, but the majority of them seem to fit quite well. So moving on to the results of the inverse for stress for this simulation, we here show that in the inversion results for the homogeneous components. The simulated post-main shock principal stress directions in this case are represented by squares. So this is what we used as input to simulate our stress. And they represent the sum of a regional stress here labeled pre-main. So it's the pre-main shock regional stress field. And they're summed together with the static stress here represented in circles. You can see that the total stress in squares are virtually the same as the pre-main shock stress. So here's a square and an upright triangle representing pre-main shock, square, triangle, and etc. Also, just to note that, when you get to the edge of one of these stereo nets, then this is, essentially the same direction as this. Oop, I did it again. Okay, and so this and this are more or less the same location. You can see that the homogeneous post-main shock stress field is dominated by the pre-main shock stress field. And that's a consequence of our simulated regional stress field being substantially larger than the static stress field, as we expected. Interestingly, the static stress changes, as you can see here by the circles, also are consistent with strike slip faulting from an Andersonian perspective, but they would imply left lateral slip on a fault oriented like the main shock, rather than right lateral slip as observed. So the average static stress as seen by the aftershocks is quite different from the pre-main shock regional stress in terms of principal stress directions. That's going to come up in a bit. The stars and inverted triangles, so stars and inverted triangles, those are the stress estimates from our study and our method and Vavricek using the fault instability constraint. And you can see that those agree quite nicely, not only with one another, but also with our target value. I did it again. Our target value, represented by the squares, that is the post-main shock homogeneous component of post-main shock stress. So, despite the differences in the methods for picking fault planes, we're nevertheless able to recover the correct answer, at least for the simulation. And you can think about the way that the stress field, why the regional dominates in these unit vectors, because if you have prior to taking the unit vector, you have a regional stress vector with a large magnitude, you add to it a small static stress change, you get a one stress direction, same static stress change, but a smaller regional stress, then you have much more sensitivity to that static stress change. It would affect the orientation of the total stress more. Okay, so and that for a simulation we can compute these things. What is the total power contributing? What is the power in the total stress deriving from the regional stress and from the static stress? And this is just showing the proportion of each. And you can clearly see that the power is dominated by regional stress, and only in one instance here are they even comparable in any way. Another way to look at this that's useful for when we're not doing simulations, because it's actually something that we can calculate without knowing what the correct answer is the relative contributions to fitting the data. And so here we're plotting the observed slip vector data versus the computed slip vector data. If in a perfect world, if we had a perfect fit, everything would lie along this 45-degree dipping line. And here are the relative contributions from the homogeneous stress, the AM part of the model, and the contrast stress, the BN part of the model, and then their sum. So the teal representing the sum does a reasonable job of matching the data. But you can see that that match is provided primarily through the AM portion. And the orange, which represents the contrast stress contribution, it's not entirely zero. You can probably pick out a slight slope here, but it's relatively small. And it might be interesting that it's not zero, which in some sense puts a loose constraint on the magnitude of the regional stress, which is something that we really don't know. We do know what the magnitude of the static stress changes is because we can calculate it, and we can calculate it with probably some reasonable accuracy. So that puts a loose constraint perhaps on the total, the magnitude of the regional stress. Another way to look at this and to think about our performance here is to compare the simulated versus the estimated contrast stresses. And we can use a measure of similarity much like a vector dot product. Here it's tensor dot product, and it again ranges from -1 for perfectly misaligned tensors to a value of 1 for perfectly aligned tensors. And despite the fact that the static stress is relatively small compared to the regional stress, we still have a number of contrast stress estimates that agree reasonably well with the simulation, but we also have some that don't. And that's probably just a consequence of some of those, the magnitude of the static stress varies as a function of space as well. So we might be in some places where the magnitude averaged over a cluster is larger, some places where it's quite small and just kind of gets lost in the noise maybe. Okay, and so what does the stress, the sort of total stress look like? So this figure shows on the left the total stress directions on a stereo net. And you can see the scatter here. I've color coded it by depth, just in the event that there was some depth dependence that emerged. I don't really see a significant pattern, But what I do see is that the primary variability tends to be between the sigma 1 direction and the sigma 2 direction. And this makes some sense because I didn't mention this before, I should have, the regional stress was created under the assumption that this parameter called the stress ratio is 0.2. And this stress ratio takes on values between 0 and 1. The value of 0 indicates that the sigma 1 principal stress value is equal to this sigma 2 principal stress value. The value of 1 would indicate that the sigma 2 stress principal stress value is equal to the sigma 3 value. And in this case, 0.2 close to 0 means that sigma 1 and sigma 2 have a slight trade-off with one another. And that sort of emerges as the scatter trade-off between these two components and relatively little or smaller variability among the sigma 3 directions. And for the contrast stress, it's just sort of all over the place. So we'll come back and talk about the contrast stress in a bit. It's perhaps worth saying here that even if the case where the regional stress is quite strong, it's still depth dependent. The stress magnitudes depend on overburden pressure. So in the shallowest parts of the crust, you might still expect that to contribute a little bit to the variability among directions, where the static stress, although small, might contribute a little bit more because just the regional stress is a little bit smaller in magnitude in the shallow crust. Okay, so now we can move on to real data. It looks like time is ticking by here really fast, and I'm got a lot of stuff to go through. So really quick here, this is real data for the RIDGECREST sequence. We'll use the same clustering. Very quickly, we get approximately this sort of same fit to the data. The variance reduction is a little bit smaller, but it's still reasonable. The estimates we get for homogeneous stress axes are shown here, and they're pretty much dead on with what we expected. Our simulated example, the principal stress is located just about 5 degrees off and north. The sigma 3 is to the east, and sigma 2 is verticals, consistent with Andersonian fault mechanics. The results from both Vavricek and our study are identical, more or less. Again, we can sort of see that the data are fit primarily by the homogeneous component of the stress. There's a little bit of a slope to the orange here, so there's some contribution from static stress, and this might place some loose constraints on the magnitude of regional stress. I haven't quite figured out how to quantify that just yet. If we look, here's when we can actually think about some scientific questions now. If we look at the, we don't have the simulated stress to compare with. We don't really know exactly how well we're doing, but we might at first think about how does the homogeneous stress field compare with the contrast stress field? Well, the contrast stress field is constructed such that if there were some components of the stress field that look similar to the homogeneous field, then there must be some other cluster that has a contrast stress field that cancels it. So it's not unexpected that this has a relatively symmetric distribution around 0 here. So that's not all clustered around 1, like these different stress fields are all the same. But the question of why such small stress changes might affect earthquakes has two answers. One is, well, maybe it's the static stress isn't what's triggering the earthquakes. Number 2 is that maybe the earthquakes are being triggered in places where the static stress field on average is aligned with the regional stress field. And this is the stress similarity hypothesis of Hardebeck. It was published in 2020. And it's illustrated by this Moore circle diagram here. The idea is that if these stress fields are aligned, then you add one to the other. The effect is that you bump up the differential stress a little bit, and this tends to increase the shear stress on fault planes of all orientations. And the thing to keep in mind with the homogeneous stress field estimates is that it includes not only the contribution from the regional stress, but also the averaged part of the static stress change field, right? So the contrast stress doesn't necessarily relate to the static stress directly. A lot of its variability derives from the static stress field because the static stress field is spatially heterogeneous, but it also has a constant part. If we were to average the stress field over the entire area, including the red places and the blue places, it might sum to zero ultimately, but we're only sampling it where we have aftershocks, and those tend to be places that have similar kind of stress. But that constant component gets absorbed into the homogeneous stress field. And so one thing that we can look at here is, we have the real data where we've estimated this homogeneous stress. We can compare it with the simulation. The homogeneous stress estimates are quite similar, but remember that the average static stress change was rotated about 90 degrees relative to our expectation. And so based on that, it seems like on average, the static stress change does not really align with the regional stress. And although this is just a simulation, it seems to be a reasonably strong argument, although it's something that we really need to look into further before we can say anything definitive about it. And then just quickly, this is the result on the real data for the stress variability. It looks very much like the result we obtained from the simulation. So now moving on to the L'Aquila earthquake sequence. The L'Aquila earthquake sequence began in January of 2009, central Italy. 4 shocks occurred for a period of about 4 months, ramping up to a magnitude 4 event on March 30th, then culminating in the magnitude 6.1 L'Aquila main shock on April 6th. Before the main shocks, 4 shocks were located along the base of the L'Aquila fault system, more specifically the Paganica fault, which is indicated here. And here we're going to focus only on the aftershocks, not the foreshocks. And we're going to assess their sensitivity to stress change induced by the main shock rupture, for which we have a detailed and well-determined slip model shown here. And again, Cassie has taken this and computed the stress changes. In exactly the same way as we did for the RIDGECREST earthquake, we'll adopt a 60 cluster model. We'll use the Gaussian mixture model to find fault planes. We obtain comparable fits to the data. The variance reduction here is a little bit smaller. This is on real data. We get something that looks reasonably Gaussian with zero mean for the residuals, et cetera. Dot products are tending to be closer to 1. And we can see here that the relative contributions of homogeneous stress and contrast stress to fitting the data is a little bit more even. There's a slight slope to both of these. And here we finally get to a strange result. Here we show the homogeneous stress estimates from our code and from Fabrichuk, and they agree quite well. This blue triangle and that blue square are more or less the same place. The principal stress, the maximum stress is vertical as expected in a normal faulting environment. However, this doesn't really fit with our understanding from an Andersonian perspective on what things should look like. In fact, it's about 90 degrees out of whack. The expectation based on the mapped faults is that we would expect the normal faults to trend in a northwest southeast direction. In fact, this stress field that we infer is more consistent with the opposite case. It's consistent with normal faulting environment, having sigma 1 in the vertical direction, but the faults are oriented 90 degrees off. So what could possibly be going on here? Several past studies have envisioned a role for high pressure pore fluids in controlling seismicity in the central Apennines. Central Apennines consist of carbonate and siliciclastic thrust sheets in place during Miocene-Pliocene convergence between the Adria promontory of the Nubia plate and Eurasia. Subsequently, quaternary extension produced a network of normal faults that accommodate extension that integrates to about 2 to 3 millimeters per year across the range. And then the normal faults now are the source of most seismicity in modern times. Subducted carbonates are thought to provide an abundant deep source of carbon dioxide. In fact, diffuse degassing of carbon dioxide is observed across a large region of central Italy, as shown in the map from GEODESY on the left over here. And CO2 gas emissions are quite high, measured in thousands of liters per second. So the larger color map in the center here is from Chiaraba et al., and it shows VP and VP-VS over VS anomalies along the spine of the Apennines, extending from northwest to southeast, so northwest to southeast. The hypocenter of the L'Aquila earthquake, our target of interest here, is located here. The study was conducted, trying to understand earthquakes that happened in 2016 and 17, shown here, these big red stars, but still useful for our purposes. Model A here represents a period from 1997 to 2017, and Model B shows results from 1997 to 2015, which is just prior to the first of these big earthquakes to occur in 2016. The VP-VS anomalies are high near the hypocenters of L'Aquila and other earthquakes. Other studies have made similar observations, and these studies have led to the development of a hypothesis by which high pore fluid pressure plays a critical role in central Italy earthquake sequences over the past 20 years or longer. The case for L'Aquila is particularly well documented seismologically. I think the earthquake occurred fortuitously during a time when there was a temporary dense deployment of seismometers, or they ran out immediately following, I guess, but I think they had instruments out before and after. And so these figures are from a study by Bakeski et al., who summarized the results for L'Aquila. They focus on 3 time periods. P1 is the period leading up to the magnitude 4 shock. P2 is the time period between the magnitude 4 shock and the main shock. And then P3 represents a time period of 46 hours immediately following the main shock. The top figure shows these VP and VS anomalies for all 3 periods, and you can clearly see a change between P1 and P2 in both of these parameters, VP and VP over VS. These anomalies have been interpreted as the signature of high pressure pore fluid released by damage associated with the magnitude 4 shock that ultimately precipitated the L'Aquila main shock. You can't see this in the figure, but the foreshocks also migrated over time at rates of meters per second, yielding estimates of hydraulic diffusivity or permeability that are consistent with laboratory results for dolostone rocks thought to be present in the source region and from previous studies of migrating seismicity. It turns out dolostones are heavily fractured and thus permeable and are thought to make excellent reservoirs capable of storing vast amounts of fluid. These rocks are capped by anhydrites in the Apennines that are impermeable, which may explain the buildup of high pressure in the dolostones. And these inferences have been corroborated by data from deep boreholes, which have actually tapped into some of these high pressurized carbon dioxide reservoirs. And so the model is summarized in the cartoon at the bottom here, which envisions a high pressure fluids permeating. So prior to the magnitude 4 shock, there was some overpressurized fluids. Magnitude 4 sort of allowed those fluids to move towards the L'Aquila fault and then subsequently ruptured L'Aquila. And then some studies envisioned that fluid then penetrated into the hanging wall over the L'Aquila fault. And so we can use our modeling scheme to test if high pore fluid pressure might explain the unexpected stress axes that we obtained from the L'Aquila aftershock data. So looking again at this earthquake sequence, but now simulating the regional stress and the slip vectors associated with that, we can build a stress model that has a very high pore fluid factor. Here, lambda represents a pore fluid factor. 1.0 here represents lithostatic pore fluid pressure. So this is a value that's very, very high. The coefficient of fault friction here, 0.6, is in the range of Byerlee friction. It's a little bit on the low side, but it's still pretty normal. Again, for this simulation, we've computed slip vectors, we added noise, we did our usual routine, we get pretty much the same plots. But you can see here immediately that the purple representing the homogeneous stress contributes very little to explaining the data, and the contrast stresses now explain almost all of the variability in the data. When we look at the homogeneous stress axes, again, we see we're tracking the squares. That's the target. It's the sum of a pre-main stress and a static stress change. But unlike previous cases, the homogeneous stress is now dominated by the static stress because the pore fluid pressures disabled the effectiveness of the regional stress. And we can see here in comparison to our previous results that we get something that kind of looks similar in some sense. We still have almost a vertical principal, maximum principal stress. And we have the sigma 3 and sigma 2 axes that are rotated relative to the pre-main stress field. And it's similar enough to the case that we get from the observed data that maybe we're onto something. And just to follow through and say, well, how well did we determine this this contrast stress? Here's a comparison, the stress similarity. It's the tensor dot product between the simulated stress field averaged over the clusters and the cluster averaged estimates that we get. And you can see that they fit pretty well. There's some that fit less well, but the vast majority of them are dead on. So the method seems to be picking up that contrast stress quite nicely. So the next question, something for future work, is to go back and look at those contrast stress estimates from Lockwell and see if they can tell us some additional information on what might have been happening during that earthquake sequence. So sorry, this talk went a little bit longer than I expected. Here's my conclusions. The bottom line is that there seems to be important information provided by aftershocks that haven't been fully tapped. Modern data sets provide us with pretty large data, data sets with which to explore things in maybe more detail now than we might have been able to do in the recent past. And I'll stop here. Thanks for listening.
All right. Thank you, Rick. We have time for a couple of questions at least. We can stay back on. So you can either type your question in the chat or just use the raise hand feature and ask your question to Rick directly. Okay, Rick, I had a question actually, and it's kind of more of a methodological question, but you have that slide explaining your k-means clustering analysis. Yeah, anyway, I was just wondering if you could just give a quick overview on the state space of those k-means. And I've kind of come across k-means in my subfield and so on, but I've never really understood it. So if you could just walk me through some of the math there, that would be great.
Yeah, okay, so the basic idea, and so we've got this function we're trying to minimize, and we've got this parameter R here, which if a dot lies in the cluster is equal to 1 and it's 0 otherwise. And so the effect of this is that we're simultaneously trying to maximize the distance between the cluster centers while at the same time minimizing the variance within each cluster. And so it's a purely objective way of trying to group data based on spatial proximity. So the data that go in here, this is only a two-dimensional example. The data that go in here are the locations of aftershocks in a local Cartesian frame. And so these distances are basically just Euclidean distances.
That can be put into multivariate space as well, right?
Sure, yeah, people use this on all kinds of different data sets, but this was a really straightforward one where we literally had spatial data and typical distance measures.
Got it, thanks.
Mm-hmm.
Okay, if there are no questions, then thank you very much, Rick. And we can call it quits right now. And remember, your talk will be posted on the Colloquium website. So thanks, Rick.
Great, thank you, everyone.